Hi everyone, welcome to this module on OCI Load Balancing Service. My name is Rohit Rahi and I'm part of the Oracle Cloud Infrastructure team. In this module, we'll look into what a load balancer is and the OCI Load Balancing Service and some of its key characteristics. Before we get into the OCI Load Balancing Service, let's look at a quick primer on what a load balancer is. As it's shown on the slide, a load balancer sits between the clients and the backend and perform tasks such as service discovery, health checks, and decides what kind of algorithms is used to balance requests across the healthy backends. So if you see here in this graphic here, there's a load balancer sitting between the clients here, and there are backend servers here. And the first thing load balancer does is it does a service discovery. It figures out what backends are available in the system. How should the load balancer talk to them? It does a health check, making sure that these servers are running. If a particular server is not running, it takes it out of the rotation, etc. What are the key benefits of using a load balancer? The first key benefit is fault tolerance and high availability. Using health check and the various load balancing algorithms, a load balancer can effectively route around a bad or overloaded backend. So if this backend is not working, requests are still coming in. Load balancer can route it to a healthy backend. The second big benefit is scale. Well, the whole idea of using a load balancer is to get higher throughput, uh, minimize response time, and avoid overload of any single resource, right? And then load balancer also does things like naming abstraction. Name resolution can be delegated to the load balancer. Backends don't need public IP address, for example, right? That load balancer, if it's a public load balancer, it can do the naming abstraction. Now let's look at the OCI load balancing service and some of its key characteristics. So the first is, of course, OCI provides load balancer as a service to give you the scale and HA required for your applications. We have a choice of public and private load balancers. Different protocols are supported. Of course, TCP, also HTTP, even the newer ones like HTTP/2 WebSockets. So the same load balancer does both TCP and HTTP. Unlike some other cloud providers, you really don't need two different flavors of load balancer, two or more different flavors of load balancer to handle your TCP and HTTP request. A lot of SSL functionality is covered, whether it's SSL termination, end-to-end SSL, things like SSL tunneling. We also support advanced features such as session persistence and content-based routing. Some of the key differentiators are, well, we have a public load balancer and you get a public IP address with it. Again, this is different than some of the other cloud providers where you just get a CNAME. When you provision a load balancer, you get a choice of shapes. So think about this as sort of a provision capacity. So you can provision for 100 Mbps, sort of a small load balancer, a medium load balancer, 400 Mbps, and a 8 Gbps. The idea is you really don't have to pre-warm your load balancers. If you provision a shape, you according to according to the load that you are going to get, your load balancer can handle your request. You don't really have to pre-warm your load balancer if you start getting a lot of load. And like I said, there's a single load balancer for both TCP layer 4 and layer 7 traffic. So let's look at the OCI public load balancer, and let's see how some of its key components work. So, well, it's a public load balancer, so it accepts traffic from the internet using a public IP address, which serves as an entry point for the incoming traffic. It's a regional service. If your region includes multiple availability domain, a public load balancer requires either a regional subnet, which is recommended, or two availability domain subnets, each in separate availability domains. We'll look into what that really means. Load balancer creates a primary load balancer and a standby load balancer, each in different availability domain, because the whole idea with a load balancer is to provide HA and fault tolerance. So the load balancer itself has to be highly available. If you just have a single load balancer running and something happens in that AD, there's an outage, there's a chance that your load balancer would stop taking incoming traffic, serving incoming traffic. So for that, your load balancer needs to be highly available as well. And like I said, it supports AD failover in case if you're using a multi-AD region, you have a primary AD, you have one AD, you're using two ADs, the load balancer can fail between the ADs in case of a outage. The way it works is floating public IP is attached to the primary load balancer, and the event of a AD outage, the floating IP address gets attached to the secondary load balancer. Let's look into each of these in more details in the next few slides. Now, very important to keep in mind, service treats the two load balancer as equivalent, and you cannot denote one as primary and the second one as secondary, even though we use that term loosely. There is no concept of a primary and a secondary here. So let's look at this example. This is, of course, a multi-AD region. Multi-AD regions always have three ADs. I'm just showing two ADs just to keep the picture a little cleaner. As you can see, the VCN is a regional service. It's running across the two ADs we have here. And then, as you can see here, we can get requests coming from the internet, and we have a regional subnet here, so it spans all the ADs, and we have created a load balancer. So when you create a load balancer, you create a copy, which is sort of the quote unquote active load balancer in one of the ADs, and the second copy gets created in AD2. This is again done for HA purposes, and you can see the failover gets created here. And then you have backends here. Backends can be in AD1 or AD2, and the load balancer can route the traffic to all the backends in whichever ADs they are running in. Now, if in the previous example we use a regional subnet, in this one we have AD specific subnet. So the only difference is now my load balancer is running in a subnet which is in AD1, and the other failover is running in another subnet which is in AD2, and my backends are in this regional subnet. So here we have a total of one and one. We have three subnets in total. Uh, if these were broken down into its own AD specific subnets, we would have four subnets here. Instead of three, we would have four. In the previous example, this was a regional subnet, and this was a regional subnet as well. So instead of four, we just needed two regional subnets. So again, depending on whichever requirement where you want to design your application, you could either go with AD specific subnets, or you could go with regional subnet. Just keep in mind, for a public load balancer, we do recommend that you use a regional load balancer, or you use a regional subnet. So let's look at some of these concepts in a little bit more detail. So the first thing is listener, which is the component which checks for incoming traffic on the load balancer's public IP. So as we said, this is a public load balancer, so it has a public IP address. Listener is sitting right here, and it's listening for incoming traffic, right? Makes perfect sense. Uh, Backend servers are application servers responsible for generating content in response to incoming TCP or HTTP traffic. So you have seen in this example, I have four backend server, right? And their job is to generate response. So request comes in and the response goes out from the backend servers. Now, there is something called a load balancing policy, which tells the load balancer how to distribute incoming traffic to the backend servers. And there's a choice of different algorithms: round robin, IP hash, and least connection. And we'll look into this in the next couple of slides. So basically, the load balancer is sitting here. Traffic is coming from outside. Now it has an algorithm here, which says, "Oh, should I distribute traffic evenly? Should I always send traffic coming from this particular client to a particular backend server?" And so on and so forth, right? And it does that. The backend set, well, the reality is you might have many backends. So to manage them as sort of one logical entity, we have this concept of a backend set. So of course you need backend servers in them. So you see the backend set here. You need a load balancing policy. We just talked about the different load balancing policy, and then you also need a health check policy. And with these three things, you configure a backend set. What is a health check? A health check basically is a test to confirm the availability of backend servers. Now, health check supports both TCP as well as HTTP level health checks. The whole idea is if one of these servers goes down, because the health check is the load balancer is constantly checking the health here. It can take out this particular backend from service and start sending traffic to other backends. So what are these load balancing policies? The first one is round robin. It's pretty straightforward. It's a default policy. It distributes incoming traffic sequentially to each server in a backend set. So if we have a server in 81 and we have a server in 82, the traffic would go sequentially to these servers in a round robin fashion, uh, and this gets repeated. The second policy is IP hash. This policy ensures that requests from a particular client always directed to the same backend server. So if a client, if on my machine I'm sending request, it would go to a particular backend and so on and so forth, right? So that's IP hash. And least connection basically means that the load balancer routes incoming non-sticky traffic to the backend server with the fewest active connections. So it's looking at which server has the fewest connection, least connections, and it sends traffic to that particular server. Now, the behavior of load balancer is different between a TCP load balancer and HTTP load balancer. And within HTTP, you have two kinds of behaviors. One is for cookie-based session persistence, and the other one is non-session persistent or non-sticky HTTP request. The first one being sticky HTTP request. So TCP considers policy and weight criteria, right? Its intelligence is limited, so it just considers the policy and the three policies you define and the weight criteria. HTTP load balancer has more intelligence. So if you use something called a cookie-based session persistence, then it forward request using cookies session info, which makes perfect sense because you have sticky sessions. So it looks at the cookie and then it makes a forwarding decision based on that. For non-sticky HTTP requests, the load balancer applies policy and weight criteria similar to how the TCP load balancer works. And again, some of these topics we cover: content-based routing, session persistence, sticky sessions. We cover in more detail in our level 200 module. So you should definitely check it out. The final thing is health check. Health check is a test to confirm the availability of backend servers. Health check is available at multiple levels. So first, it's available for the backends. The backends make the backend set, so there is a health check for that, and then there is a health check for the overall load balancer. So what does it look like? Now, one thing to keep in mind is load balancer can have up to 16 listeners, and these listeners are nothing but port numbers. So you can have a port 80, you can have a port 443, and so on and so forth, right? Um, each listener has a backend set that can have 1 to n backend server. So what does it look like? Well, you have load balancer IP here. Let's say this is a public load balancer we are talking about. And then right here you have listener 1, you have listener 2, and so on and so forth, right? You can have up to 16 listeners. Each of these listeners can have a backend set. Uh, so in this case, there's a backend set 1, and this backend set 1 has 3 different servers. This listener can have another backend set. It can have 2 different servers here, right? So your health check is available here, here, here. It's also available at the backend set level, and then it's also available at the overall load balancer layer level. So you have this sort of different levels. You can check if any of these checks are failing, and then you can troubleshoot and figure out why they are failing, right? Health API, the which is behind the health check, provides a 4-state health status. So there is okay, which means everything is good. There's a warning, there's a critical, and there's an unknown. Critical means for some reason the backends have an issue, and it's not working. Unknown means sometimes you would see that the status goes to unknown. So it means that, let's say, if you are using HTTP health checks, but you haven't configured your response URL. So it would return an unknown because it has no way to figure out how to get a response back, right? And so on and so forth. You can read more about these in the documentation. Now, one thing to keep in mind: health status is updated every 3 minutes. No final granularity is available to wait that period to get the health information. So with that, that's all I wanted to cover in the first module on load balancer, specifically public load balancer. Thank you for watching this module. In the next module, we'll quickly take a look at public load balancer in action. Thank you.